With each interesting picture captured by the James Webb Space Telescope, it continues to collect insights from different corners of the universe, including planets within our own planetary system. A year earlier, we considered our most significant brief look at images showing the Carina Cloud, the Southern Quintet, and, notably, the captivating Deep Field image. This express image clearly depicts various galaxies resting in the vastness of the universe, fulfilling the assumptions made. The James Webb Space Telescope hasn't stopped being a labyrinth. It has indeed revealed objects that challenge deeply grounded cosmological theories. These surprising discoveries are now being named universe breakers by cosmologists, confounding established specialists with their ability to challenge existing concepts. The reasons for these discoveries remain shrouded in mystery, throwing our hypotheses and speculations into confusion. So, what's the latest scoop from the James Webb Telescope? What extraordinary new revelations has it uncovered that were previously unknown to us? Join us as we delve into the discoveries of how the James Webb Telescope has introduced evidence suggesting the presence of another universe, challenging the standard understanding of the Big Bang. Our universe, as we've long understood it, emerged from a hotter, denser state through a theory known as the Hot Big Bang. This concept, a significant scientific achievement throughout the past century, gained overwhelming support during the 1960s with the discovery of the cosmic microwave background, CMB, a remnant from the early hot and dense state. Over time, the Big Bang has remained the dominant theory explaining the origins of our universe. However, new and crucial observations have led cosmologists and astrophysicists to reconsider both the ongoing expansion and the Big Bang itself. Despite these challenges, alternative theories have failed to gain traction, with the enduring nature of the hypothesis regarding the universe's origin continuing to prevail. According to the prevailing view, the universe's beginning involved a smaller, denser universe in the distant past. The presence of radiation, like photons, indicates that the universe was hotter at its inception and has since cooled. Extrapolating backward in time, the density, temperature, and energy levels would have reached a point where a singularity could form, and the regular laws of physics would break down around 10 to the power of -43 seconds. In such a brief span of time, with minuscule distances, brief timescales, and high energy levels, our understanding faces serious challenges. Rewinding the cosmic clock to the theoretical zero point, if the universe began as hot and dense, it would have expanded and cooled, creating vast quantities of particles and antiparticles. Excess particles were destroyed by radiation as temperatures decreased, leading to the breakdown of the weak and strong nuclear forces and the formation of the four fundamental forces and particles with non-zero masses. As the universe cooled further, protons and neutrons combined to form composite particles, such as quarks and gluons. The combination of protons and neutrons led to the creation of light nuclei, such as deuterium, helium-3, helium-4, and lithium-7. Overdense regions expanded due to radiation pressure, followed by gravitational collapse, leading to the formation of large-scale structures. Around 380,000 years after the Big Bang, the universe cooled enough for stable neutral molecules to form, marking a significant step where photons decoupled and their frequencies stretched as the universe expanded. The discovery of the cosmic microwave background, many years ago, cemented the theory of the Big Bang as the most supported explanation for the universe's creation. #### Big Bang versus steady state theory. While most cosmologists and astrophysicists embrace the Big Bang theory, resolute defenders of the steady state theory, such as Fred Hoyle, continue to support increasingly dubious ideas, only to face rout in the face of overwhelming evidence. The evidence presented was definitive, not blurred starlight or reflected heat from dust, but the cosmic shine displayed an amazing consistency resembling an optimal black body, yet it had no affiliation with known objects in the universe. Despite this, Hoyle and his supporters continued to undermine scientific progress by advocating for scientifically unwarranted ideas. In the meantime, fields like space science and cosmology experienced significant progressions from the 1960s through the 2000s, with cosmology making especially notable advances. We mapped the universe, described its enormous scale structure, and investigated the formation, evolution, and dynamic interactions of galaxies and their stellar populations. Even with these advances, anomalies persisted that challenged explanations within the framework of the Big Bang theory. Notably, the absence of expected relics such as magnetic monopoles or particles from grand unification led many to reconsider parts of the theory. The universe we observe today seems to require forces beyond our current understanding. At its beginning, the universe required a precise rate of expansion to balance the overall energy density, something the standard model of cosmology struggles to account for. This led to neither perfect harmony nor sufficient time for energy exchange across various regions of space. Given the vastness of the universe and its expansion over time, these inconsistencies present significant challenges to cosmology and mainstream scientists. ### the inflationary model and its challenges. While existing speculations fail to account for observed irregularities, two approaches have emerged: refining current theories or considering alternative explanations. The theory of inflation has emerged as the most promising framework to expand the Big Bang perspective. Inflation proposes a brief period of rapid expansion that smoothed the universe, giving it uniform properties. It addresses the horizon problem and predicts the development of quantum fluctuations, which manifest as density and temperature variations. The predictions of inflation align with observed patterns and changes, supporting its validity. Despite alternative hypotheses, inflation's scientific strength remains unparalleled. However, despite past contributions to general relativity and singularities, Roger Penrose's work, along with his cooperation with Stephen Hawking, failed to match the development of inflation in explaining the earliest moments of the universe. Recently, focused work has been done to challenge the legitimacy of inflation theory, supporting formal cyclic cosmology. However, this theory is inherently flawed from a scientific standpoint, as the key distinction lies in their predictions. Conformal cyclic cosmology suggests that remnants from a universe preceding the Big Bang are etched in the cosmic microwave background and the large-scale structure of the universe. On the other hand, the inflationary theory maintains that the end of inflation and the hot Big Bang are causally detached from any pre-Big Bang era. ### James Webb Telescope's astonishing discovery. Researchers quickly recognized anomalies in the images sent by the James Webb Space Telescope since 2022. These revelations may require a reassessment of key aspects of the universe's beginnings and evolution. One significant discovery made by the Webb telescope was the presence of fully formed galaxies much sooner than expected by the standard cosmological model. This anomaly challenges the established sequence of events following the Big Bang, where stars and black holes form first, followed by galaxies. Such discoveries disrupt our understanding, similar to experiencing grandparents depicted as children in a story. Additionally, recent evidence has uncovered anomalies within the major theories of the universe, such as the persistent error in determining the Hubble constant, which continues despite improvements in data precision and collection methods. New data from Webb continues to challenge the current cosmological model. These issues highlight flaws within the model, raising questions among researchers and physicists. While the model has undergone adjustments to align with emerging data, some argue that these changes have been too accommodating. As a result, there is growing recognition that a shift in perspective might be necessary, potentially reshaping our understanding of the universe's fundamental properties. The standard model of cosmology, hailed as a triumph of human knowledge, arose from Edwin Hubble's monumental discovery of the expanding universe during the 1920s. Subsequent discoveries, such as the detection of the cosmic microwave background radiation in 1964, confirmed the Big Bang theory as the most plausible explanation for the universe's beginnings, depicting the early universe as a hot, dense soup of subatomic particles gradually cooling over time. ###rethinking cosmology. Achieving the current level of accuracy in cosmological understanding has required theoretical extrapolation beyond observational data. The possibility of infinite expansion, presented in 1981, was introduced to resolve inconsistencies in earlier Big Bang models, further emphasizing the dynamic nature of cosmological theory. According to this model, the early universe underwent rapid, extraordinary expansion shortly after the Big Bang. While specific issues are resolved by this theory, new challenges emerge, especially given the prevailing belief in the existence of a single universe. Perhaps there are countless others beyond our observational reach. Several identifiable anomalies, such as singularities inside black holes, find support through indirect evidence. However, the stunning revelations from the Webb Space Telescope regarding the formation of galaxies and the ongoing issues with the Hubble constant raise concerns that we may be approaching a tipping point where a major revision of our current cosmological model becomes necessary. This could require a complete reassessment of the fundamental building blocks of the universe, including the very nature of existence itself. Cosmology, unlike many other scientific fields, deals with fundamental questions about the universe, its origins, and our place within it. The study of consciousness and quantum physics also explores similar subjects, examining the intersection of theory and reality. It is crucial to question these essential assumptions, given the impact of theoretical presuppositions on data collection. History has shown that shifts in scientific thought, such as the transition from geocentrism to heliocentrism or the discoveries of evolution and relativity, have led to profound changes in societal perspectives. A similar shift in our understanding of the universe may be forthcoming due to an impending scientific revolution in cosmology. Philosopher Robert Anton Wilson contends that theory becomes essential when further scientific inquiry fails to provide satisfactory answers to a question. New research into cosmology may ultimately lead to the collapse of the current model, not due to empirical falsifications but due to its failure to fully embrace new paradigms that reflect the latest findings. The current narrative must, therefore, be reconsidered in light of new evidence as the James Webb Space Telescope continues to unearth revelations that may forever alter our understanding of the cosmos. Neil deGrasse Tyson, a renowned astrophysicist and science communicator, made headlines with his comments on the James Webb Space Telescope, JWST, in relation to the discovery of evidence pointing to the possibility of another universe. The JWST, launched in December 2021, is a powerful space telescope designed to explore the cosmos in infrared wavelengths, allowing scientists to look further into the universe's past than ever before. Tyson's remarks stem from the incredible discoveries the JWST is already making, particularly in areas such as the formation of the earliest galaxies, stars, and exoplanets. While Tyson didn't directly claim that the JWST has found proof of an alternate universe, he was referring to some of the surprising and unexplained phenomena observed by the telescope, which could hint at something beyond our current understanding. One such phenomenon is the existence of unusual, unexplained structures in the distant universe, which may suggest that the laws of physics as we know them could be different in other parts of the cosmos, or that the universe itself could be far more complex than we had previously imagined. This could imply the presence of other universes, as suggested by some theories in cosmology, such as the multiverse hypothesis. However, it is important to note that while these observations are intriguing, they do not yet provide concrete evidence of another universe. Instead, they open up the possibility for new theories and ideas that could redefine our understanding of space, time, and reality itself. As the James Webb Space Telescope continues to provide unprecedented views of the universe, it challenges long-held assumptions about the cosmos. The telescope's ability to observe galaxies in their infancy, light from the early universe, and far-off exoplanets has brought new insights, but it has also raised questions that could reshape our understanding of the universe's origins and structure. These revelations underscore how much more we still have to learn about the cosmos and the fundamental laws governing it. One of the most intriguing aspects of Webb's discoveries is its examination of galaxies that appear much more mature than current models of cosmic evolution predict. The formation of large, fully developed galaxies so early in the universe's history suggests that processes previously thought to take billions of years may be occurring at a much faster rate. Some researchers believe these findings could force a re-evaluation of how galaxy formation works, potentially unveiling new mechanisms or undiscovered variables at play in the early universe. Another mystery Webb is investigating is the formation of the first stars and black holes. These objects, thought to have formed in the very early stages of the universe, are crucial for understanding the transition from the cosmic dark ages to a more structured, light-filled universe. Webb's ability to peer deeper into space than ever before allows scientists to study these objects in more detail, revealing anomalies that could force a shift in how we think about the first billion years of the universe. Webb's observations of exoplanets are equally groundbreaking. By studying the atmospheres of planets outside our solar system, the telescope is providing valuable information that could one day help identify habitable worlds beyond Earth. This data is also adding to the ongoing debate about the potential for life elsewhere in the universe. Some findings hint at the presence of strange chemical signatures in the atmospheres of distant exoplanets, raising the possibility that these worlds may host life forms that are vastly different from those on Earth. The anomalies observed by Webb are not limited to distant galaxies or exoplanets. The telescope has also observed peculiar features within our own galaxy, such as irregularities in the cosmic microwave background, CMB, radiation, and surprising variations in the distribution of dark matter. These unexpected findings could be indicative of new, unknown forces or phenomena that remain hidden within the fabric of space-time. The inconsistencies observed in the CMB, in particular, may force cosmologists to revise their understanding of the universe's large-scale structure and how it evolved from the Big Bang to its present form. Despite the excitement surrounding Webb's discoveries, many scientists remain cautious. While the telescope has provided incredible data that may lead to groundbreaking revelations, interpreting these results is complex. Many of the anomalies are still in the early stages of analysis, and it may take years of additional study to fully comprehend their implications. As a result, while Webb's findings are expanding the boundaries of cosmology, they also highlight just how much remains to be discovered about the universe's past, present, and future. What is clear, however, is that the James Webb Space Telescope has the potential to revolutionize our understanding of the cosmos. Its ability to peer into previously unreachable corners of space is opening up new frontiers in astrophysics, pushing the boundaries of scientific knowledge and sparking a new wave of curiosity about the universe's origins and its ultimate fate. As researchers continue to analyze its data, the telescope will undoubtedly play a pivotal role in the next great leap in our understanding of the universe.